Hello, everyone. This is Perfil, an application engineer at Bettersize Instruments. Today, in this presentation, I would like to show you the fundamentals of an automatic gas pycnometer, the BetterPyc 380. We call it the BetterPyc for short. There are 3 parts to this presentation, each with a question. With the first question, what is the true density of powders? You can understand factors that affect the powder density. Classify the powder density, have the answer of what is the true density, and further realize its significance in a wide range of industries. Second question is how to determine the true density. This part explains 2 main methods to determine the true density. One is the water displacement method, and another is the gas displacement method. By comparison of the 2 methods, you will have a better idea to choose a suitable method to measure your sample. Taking the third question, why is the gas pycnometer BetterPyc? I'm going to introduce its hardware and software in detail, and then the features and benefits will be revealed. Application cases from various materials demonstrate its versatility and high accuracy. In the end, you will know how to select a suitable packaging for BetterPyc to start your research. Now, let us start with the first part. What is the true density of powders? Before answering the problem, I would like to discuss the concept of density. As we all know, density is defined as its total mass divided by its total volume. It is a crucial physical property that can provide information about the composition and behavior of materials. When it comes to bulk substances, such as glass beads and steel, measuring the density is relatively simple. The most common method is to use a ruler to measure the dimensions, such as the diameter of a ball, and a balance to measure its mass. Once you have the mass and volume of the sample, you can calculate its density by dividing the mass by the volume based on the formula. It is easy, right? However, measuring the density of powder samples is more challenging compared to bulk samples. A powder consists of a mass of irregular and individual particles, for example, coffee powder, sand, and soil. There are several factors that can affect powder density. These factors are divided into primary factors and secondary factors. Primary factors include particle packing, particle size and distribution, particle shape, and internal pores. Particle packing. A tighter packing arrangement will result in a higher powder density. For instance, rhombohedral packing leads to a higher density than cubic packing. Particle size and distribution. A wide particle size distribution increases the likelihood of fine particles migrating into the void that is formed between larger particles. Therefore, a system with a wider particle size distribution will form a structure that is less void. Particle shape. Irregularly shaped particles can have more voids between them, leading to a lower powder density. Internal pores. Pores within the particles can create voids in powders, leading to a lower density. In addition, compaction, moisture, and temperature as secondary factors should be taken into account. It is these factors to make a determination of powder density complex. To obtain accurate results, we should understand the volumes occupied by solid materials and pores in a powder, and then choose a suitable apparatus to measure volume or density. In general, a powder sample consists of 4 types of volumes that contribute to its overall volume. Solid materials. These are the solid particles that make up the powder. Closed pores. These are pores within the particles disconnecting to the atmosphere. Open pores. These are pores within the particles connecting to the atmosphere. Interparticle pores. These are voids between the particles that result from their irregular shape and packing arrangement. The true density is the density of just the solid materials and ignores any pores. The skeletal density is the density of the solid materials and the closed pores. The bulk density or tap density is the density of the solid materials, the closed pores, and the interparticle pores. Essentially, the difference comes down to the sample volume that is used in the expression. So, depending on the powder density to be determined, the corresponding volume must be measured accurately. If you learn more about how to determine tap density and bulk density, you can click the link to Bettersize YouTube channel. The BetterPyc can determine true density or skeletal density, which is important in a broad number of industries. In powder engineering, the void fraction is an important property, as it can affect the flowability, compressibility, and stability of a powder sample. Void fraction refers to the ratio of the volume of pores to the total volume of a powder sample. There are two kinds of void fraction. The total void fraction is the total volume of all, divided by the total volume of the sample. The effective void fraction is a measure of the accessibility of the pores within a powder sample and is defined as the volume of accessible pores, divided by the total volume of the sample. The effective void fraction, in particular, provides a measure of the accessibility of the pores within the sample, and is often of greater interest to powder engineers. Based on the formula, skeletal density is an essential parameter to determine the fraction. The solid content of a slurry is an important property that can have a significant impact on the performance and quality of the final product in many industries. It refers to the amount of solid material in a slurry, typically expressed as the following formula. Basically, the volume of a slurry is equal to the volume of solid materials and the liquid phase. By the mathematical transformation, we can get the relationship between density and solid content. Based on the relationship, if we know the liquid density, solid density, and slurry density, we can calculate the solid content. Rigid foam has a similar porous structure to powders. As we can see, the foam has closed cells, open cells, and cell walls. We can measure the different volumes of foam to study their properties. The open cell content refers to the percentage of the geometric volume of the foam that is occupied by open cells. It has a direct bearing on its end use. To determine the open cell content, we can measure the skeletal volume and the geometric volume of foam samples according to the formula. Furthermore, the closed cell content can also be determined if we know the mass and specific gravity of the materials in a solid foam. By the first part, we know the definition and significance of the true density. Now, move to the second part and explore how to determine it. The first is the water displacement method, which is a common technique for determining the true density of a solid object. This method is based on the principle of Archimedes' law. The law states that the buoyant force experienced by a submerged object is equal to the weight of the fluid displaced by the object, expressed as this formula. To use this method, you first need to measure the mass of the object in the air using a balance. Next, hang the object from a balance and place it in water. Then carefully measure the weight of the part in liquid. Once you have measured the mass of the object and the part in the fluid, you can calculate the true density using this formula. The second is the gas displacement method, known as gas picnometry, which is based on Boyle's law. The law states that, for a given mass, at a constant temperature, the gas pressure times the volume is constant, as expressed in this formula. To make it easier to understand, let us take an example. There are two chambers, a pressure transducer, and a valve between the chambers. On the first condition, the valve is closed, the gas just fills up the left chamber, and we get the volume as V1 and pressure P1. Open the valve to allow the gas to flow into the right chamber. We get the volume V2 and pressure P2. Apply the Boyle's law. The P1 times V1 is equal to the P2 times V2. With this understanding, come to a real picnometer gas system. As shown in the diagram, this system consists of two chambers, the sample chamber and the reference chamber, both with an extremely precise and known volume. A pressure transducer is located in the sample chamber to measure pressure changes. Additionally, the system is also equipped with three valves, a fill valve, an expansion valve, and a vent valve, that are used sequentially to regulate the flow of gas through the system. To start analyzing your sample, the first step is to place it in the sample chamber and fill the chamber with gas by just opening the fill valve. It takes some time for the pressure to equilibrate at a specific change rate, and the pressure is then recorded by the pressure transducer as the value P1. The gas volume is calculated by subtracting the sample volume from the sample chamber volume. In this condition, we get the first relationship between the pressure and the volume of gas. After that, the expansion valve is open to allow gas to extend to the reference chamber. You also need to wait again for the pressure to equilibrate at the same rate as before, and record the pressure reading as P2. In this case, the gas volume is the volume of the sample chamber and the reference chamber minus the sample. In the expanded condition, we get the second relationship. These two relationships are rearranged by applying the Boyle's law. Now we get the calculation of the true density. So, which method is suitable for determining the true density of your sample? In the comparison of the two methods, we can find that, in the water displacement method, a liquid such as water or oil is used as the analysis medium, while a gas such as helium or nitrogen is used as the analysis medium in the gas displacement method. In terms of sample requirements, in general, the gas displacement method is suitable for water-absorbent and hydrophobic samples. This is because the gas can displace or penetrate most of the materials, and the true density can be accurately measured. In terms of resolution, the gas displacement method is generally more precise and accurate, with better than 0.001 gram per cubic centimeter resolution and less than 0.3% relative standard deviation. Overall, the gas displacement method proved a more widely used and accurate approach to measure density. Next, I will introduce an automatic gas pycnometer BetterPyc, based on this method in Part 3. In this part, you can realize the BetterPyc 380 is a versatile gas pycnometer with high accuracy. Okay, it is time for Part 3. Why the BetterPyc? The hardware and software of the instrument will be presented. Start with the hardware. The main device is fully automatic and can be operated using the software developed by Bettersize. In Part 1, you saw that keeping temperature stability is pretty important in the gas pycnometer system. The inside water path system of the BetterPyc is a key feature. Based on it, the external recirculating water bath can ensure temperature stability and accuracy during measurements. The water bath can be monitored and modified using this software. The multi-volume cups are in a wide range of volumes, including 100, 35, and 10 cubic centimeter, and the operator can choose the best configuration for their specific application. Lastly, the gas pycnometer is equipped with a Bettersize certified calibration standard to ensure the accuracy of chamber calibration. In the inside gas system, we can find that there are some differences with the basic pycnometer system. Exactly. The gas system of the BetterPyc is improved by elaborated designs for high performance. The valve is able to control gas flow through the system. The easy-to-close chamber lid supports the well-sealed conditions. A high-resolution transducer ensures precise pressure measurement. We can see here, the dual reference chambers boost the accuracy of the result. The built-in vacuum pump can clear your sample before measurement. Finally, the water from the external water bath flows into the water path, wrapping around the surface of the gas system, and that keeps the measurement at a specific and stable temperature, between 15 to 55 centigrade. In the entire testing process, the temperature and pressure are controlled and measured automatically by connecting the software. Okay, go to the software. We call the gas pycnometer software EasyPyc. There are 5 parts in the main interface of EasyPyc. Automatic functions. This section includes 3 main automatic functions: detection, calibration, and testing. These functions help to automate the measurement process, making it easier and more efficient for the user. Running parameter. This section allows the user to check the sample information and test conditions during the testing process. It provides detailed information about the parameters that are being used for the current test, including sample mass, pressure, temperature, and any relevant settings. Running status. This section displays the current running status of the instrument, including system temperature, gas pressure, equilibration, and elapsed time. This information is important to monitor during the measurement process, as it can affect the accuracy of the results. Results list. This section displays a list of all previous test results. The user can select a specific test record, volume calibration result, or tightness detection result to review. Detail results. This section provides a detailed analysis of the current or historic test results. It includes information such as data tables, graphs, and statistical analysis. This information is useful for troubleshooting and understanding the results quality. Frankly, the EasyPick provides a user-friendly and efficient way to measure and analyze data. The running display section allows you to monitor the current test conditions such as temperature, pressure, and measurement processing cycle by cycle. Once a cycle analysis is complete, the measurement result is displayed in real time. During calibration, testing, or leak detection, the running display section allows you to monitor the automatic progress. For example, as shown in the video, you can see the progress of leak detection and identify any problems that occur. Report options provide a simplified or detailed report as required. The operator can customize the analysis conditions and quickly configure them to meet your specific requirements. The balance configuration feature offers one-click saving of the mass in the software, eliminating errors caused by manual entry. The temperature control feature gives you the ability to control and set the temperature of the external water bath in the software, making measurements more convenient. Finally, you can easily keep track of your test progress with real-time measurement displays, progress indicators, and customizable report templates. The combination of the elaborate hardware and software of the BetterPyc brings each user an exceptional experience. First, the BetterPyc is a versatile gas pycnometer for 4 measured parameters. It can measure the volume and density of solid, liquid, and semi-solid materials with high precision and accuracy. Additionally, the BetterPyc can be used to determine the solid content of slurry and the open cell content of plastic foam. And another one of the key advantages is its high performance, which provides excellent resolution, accuracy, and repeatability. The instrument also offers temperature stability and efficient measurement within 3 minutes per cycle. Moreover, the BetterPyc features full automation and a temperature control system, making the measurement process more convenient. And with user-defined templates and a wide volume capacity of sample cups, the BetterPyc can be customized to meet specific measurement needs. The instrument is ideal for a wide range of industries and complies with ASTM and ISO standards relating to powder metallurgy, refractory materials, pharmaceuticals, and so on. For instance, in powder metallurgy, the engineer can determine the properties and performance of the metal products by measuring the skeletal density. With high performance, the BetterPyc provides reliable results for researchers and engineers from various industries. Then, I'm going to show you some application cases from 4 measurements: volume, density, solid content, and open cell content. In volume measurement, we use the BetterPyc to determine the volume of the bulk materials, standard ball, powders, glass bead, the porous material, coral, and the liquid sample, water. The standard deviation of the measured volume of 4 different samples is less than 0.004 cubic centimeter. So, the BetterPyc can give you accurate volume testing, which is a precondition to ensure the accuracy of other measurements. Density measurement is an essential part of materials analysis in many industries. We have evaluated the density of various materials using BetterPyc, including bulk, powder, porous, and liquid materials. The table shows the density data of 5 samples, including bulk steel, alloy powder, clay, cement, and water. The standard deviation of the 5 measured sample densities is better than 0.002 gram per cubic centimeter, indicating that BetterPyc can give you accurate density measurements, whether your sample is solid, powder, or liquid. Besides, in many industries, measuring the solid content of the slurry is an important step in the production process. In this experiment, we use the BetterPyc to measure the solid content of a clay slurry. About the experimental procedure. First, prepare the clay slurry sample and put it in a 100 ml cup and close the chamber with the lid. Next, use the BetterPyc to measure the volume and density of the sample at 20 centigrade degree. The table below shows the expected and measured results of the solid content of the clay slurry sample. The relative error of the measured solid content is less than 3%, which indicates that the BetterPyc can be used to accurately measure the solid content of slurry samples. Fourth measurement. The open cell content is an important parameter for characterizing the foam's properties. In this experiment, we aim to measure the open cell content of 3 different rigid foams by correcting the opening during specimen preparation. The table below displays the open cell content of the 3 foams: black foam, gray foam, and white foam. The corrected measurement accounts for the openings present during specimen preparation. The results measured by BetterPyc show the open cell content of foams with a large number of opening pores. This information is important for optimizing the processing techniques and understanding the mechanical and thermal performance of the foam. In this slide, we will introduce you to how to select the right BetterPyc model for your research and production needs. The BetterPyc 380 is the standard model for measuring the volume and density of different state materials. If you need to determine the solid content of slurry samples, we recommend the BetterPyc 380S. For studying the open cell content of foam specimens, the BetterPyc 380F is the right choice. And if you need all of these functions, we suggest selecting the BetterPyc 380SF model. So, depending on your specific requirements, you can easily pick the best suited model for your research and production. By now we have gone through all the sections of this presentation. First, we got the answer to what is true density, then explored how to determine it, and finally, understood why the BetterPyc is used to start your measurement. Well, that brings us to the end of this presentation. I hope you enjoyed this video. Please feel free to leave any comments or questions below, and visit the Bettersize website for more information. Thanks for watching.